On top of this, there had to be a very narrow range of temperatures, in this case supplied by the sun. This means that the sun has to be very stable and not flap up and down in its temperature, and the orbit of the Earth around it has to be very nearly circular. If gravity were a little weaker, we'd have lost all our atmosphere, like the moon. If it was much stronger, we'd break every time we fell over, and without that layer of ozone above our heads, we'd be exposed to deadly ultraviolet radiation. However, we mustn't read too much into this. The probability of being dealt a particular hand of cards, if you work it out in advance, is very, very tiny. The odds against predicting it are astronomical, but once it's dealt, we don't regard it as a miracle, of course. Only lucky if we happen to win with it. In any case, evolutionists would argue that man evolved to suit the conditions about him, and not the other way around. The really amazing thing is not that life on Earth is balanced on a knife edge, but that the entire universe is balanced on a knife edge. You see, even if you dismiss mankind as just a mere hiccup in the great scheme of things, there's still the fact that the entire universe seems unreasonably suited to the existence of life, almost contrived, we might say a put-up job.
What is at issue concerns the hidden, vital complex of particles and forces, the nuts and bolts of the universe that shape it and hold it in existence. Some of them, like the many so-called constants of the universe, may seem of interest only to those mathematicians, physicists and cosmologists who delight in them. Not so. Unless every element in this underlying foundation interlocked precisely, there would be no universe at all.
The starting point of these ideas is to decide how important or unimportant mankind, human beings, are in the scheme of things. And there's a very remarkable discovery of the last few years, which at first sight suggests that human beings are very important. And that's what we call the fine-tuning of the universe. It turns out that if you change just a little bit the laws of nature, or you change a little bit the constants of nature, like the charge on the electron, then the way the universe develops is so changed that it's very likely that intelligent life would not be able to develop.
If we nudge one of these constants just a few % in one direction, then stars burn out within 1 million years of their formation. No time for evolution. And if we nudge it just a few % in the other direction, then no elements heavier than helium form. So no carbon, no life, not even any chemistry, no complexity at all. And if we could alter the relative masses of 2 of the subatomic particles, the proton and the neutron, by just a fraction of a %, atoms would be unstable. There'd be no stars, no light, no warmth, no structure at all, just chaos.
Well, take, for example, the so-called Big Bang, the thing that started the whole universe off. And that just wasn't any old bang. It was an exquisitely orchestrated affair, so that it's precisely uniform as we look around us in space. Now, if that bang had been less powerful, the whole thing would have come out and then collapsed back into a big crunch and gone out of existence long before now. On the other hand, if the bang had been more vigorous, everything would have been flung apart and completely dispersed, and no galaxies would have formed, and we wouldn't be here to talk about it. It turns out that when you look at the rate at which the universe is expanding, it's precisely on the dividing line between these 2 unpalatable alternatives.
So the starting point is something where we're all agreed that unless the laws of nature and the constants of nature are pretty well what we find them to be, it will be impossible for intelligent life as we know it to develop, and certainly for me to develop. The controversy begins when we try and decide the significance of this agreed fact.
In order to predict the values of the fundamental constants, we don't have to use the existence of man. We could invoke a crocodile principle, if you like, that from the existence of crocodiles or of dragonflies or any other form of life, we could equally well use that to predict what the constants are. So the real motivation behind the anthropicists, if we like to call them that, the people that subscribe to this anthropic principle, is that they already have an initial prejudice to put man back at the center of the universe. And then they're bringing along arguments dressed up as scientific arguments in order to buttress what they already initially believe anyway.
Now, that certainly doesn't include me. I am sympathetic with the anthropic principle for reasons that have nothing to do with that. It's for reasons that come out of physics.
And some of those reasons do seem compelling. In the 1950s, well before anyone had invented the anthropic principle, Fred Hoyle was working out how the elements of which we are made were created in the nuclear furnaces inside stars. Stars are mainly hydrogen and helium, the simplest atoms of all. For the star to make carbon, 3 of its helium nuclei have to collide. Snooker players will tell you that happens very rarely. Far too rarely for the star to produce all the carbon we need in our bodies. But when 2 helium nuclei combine, if there's another helium close by, something strange happens. It's as if the target gets much fatter. So the likelihood of the 3rd helium homing in on the right spot to make carbon is enormously increased. No other elements behave like this. This unique stroke of utter chance has enabled stars to manufacture enough carbon for our bodies. But that's only half Hoyle's story. If another helium hits the carbon, it'll produce oxygen. So why is there enough carbon left for us? Once more, nature has made a unique and fortunate choice. This time, the reaction is so far off-tune to the energy available that only half the carbon is changed to oxygen. What were Hoyle's conclusions? A common-sense interpretation of the fact suggests that a superintendent has monkeyed with the physics, as well as chemistry and biology, and that there are no blind forces worth speaking about in nature. I do not believe that any physicist who examined the evidence could fail to draw the inference that the laws of nuclear physics have been deliberately designed with regard to the consequences they produce inside stars. Frank Tipler's comment?
A better explanation is the strong anthropic principle. The universe had to bring intelligent life into existence at some point in its history.
That's right. But this does, of course, raise the other question. If there's been enough time for man to evolve, what's the chance of there having been life of other kinds evolving around other stars? As an astronomer, I would suspect that there are many other planets around other stars that provide a propitious environment. But we can't really say whether life is likely to be unique to our Earth or whether the universe is going to be teeming with life.
Frank Tipler argues differently. We have already sent exploratory probes out into space. Our galaxy is billions of years old, so if it were teeming with life, we'd have expected many visits by now.
So, I conclude that if there are intelligent beings that have anything like our motivations, we want to colonize, we want to explore, we want to learn what's out there, that they would have long ago launched probes or launched colonizing spaceships that would have reached our solar system. Since they are not here, I don't think they exist.
Brandon Carter reaches the same conclusion by a different route.
Remember, the sun generates heat by thermonuclear fusion of hydrogen, and astronomers estimate that the hydrogen is already about half used up. This means that if biological evolution had gone just half as fast, our human state would never have been reached before the sun burned out. But now, why should processes in the sun have any tie-up with the biological processes of evolution? I can only understand this as an anthropic self-selection effect. It seems that we only just made it, and this suggests that though there may be billions of planets suitable for the formation of life, few would have achieved it.
Whichever way you look at it, the anthropic principle seems well named. Forget other intelligences, the universe may well have given rise to man alone, and of course Professor Redhead's crocodile.
Yes, of course, all these special features of the universe gave rise to the crocodile. They also gave rise to that statue behind me, as well as us. But we have something that the crocodile and the statue don't have. We understand the laws of physics. And it is understanding that the anthropic principle makes into a key feature of the universe.
It's a puzzling and I think rather non-trivial thing that we can discover so much about the universe. We are, after all, part of the universe. So we have a system which is developing according to the laws of nature. Localized complex systems like human beings develop with brains. And lo and behold, using those brains and using physical systems which obey the laws of nature to investigate nature, we can find out what those laws are. That's an amazing thing, and I think the full significance of the fact that the structure of the world permits that to happen is not at all clear.
Why should the laws of the universe be understandable by us? Well, either it's a fantastic coincidence, or there's some deep reason why it had to be that way. And if it had to be that way, then we occupy a very special place in the universe indeed.
How special was not fully realized until recently. Newton's theories of motion had been so successful in describing the orbits of the heavenly bodies that it was natural for physicists to try to apply them to the atom. After all, atoms do seem to resemble the solar system, with the central atomic nucleus as the sun and the orbiting electrons the circulating planets. But in the 1920s, physicist Niels Bohr found that Newton's laws break down at the atomic level. The replacement quantum theory, one of the most successful scientific theories of all time, showed that the electron orbiting the atomic nucleus doesn't look like this at all. It's more smudged out, more like a ripple or a wave, a graph showing where the electron probably is. We can only find out where the electron actually is by taking it out of the atom and throwing it up against a measuring instrument like a scintillation counter. The instant we see the result, the wave describing where the electron probably is becomes like Professor Davy's tiny probability of a hand of cards that is now actually dealt. It collapses to a definite statement. I see that the electron is here. We have to record some kind of measurement to know where an electron is. In fact, until we decide to find out where the electron is by doing an experiment to observe it, the electron as a material entity cannot really be said to exist. It was Bishop Berkeley who coined the phrase, "To be is to be perceived." In the tiny world of the atom, this is no religious or philosophical statement. Many scientists now believe observation to be the fundamental basis of existence. John Wheeler was a colleague of Bohr and Einstein.
Some years ago, I found myself playing the game of 20 questions after dinner with a dozen friends, and one by one we had our turn to be sent out of the room and be let back in to guess the word that everyone else had picked on. But in my case, I was shut out the longest time. And when I was let back in, everybody had a grin on his face, the sign of some joke or trick, I was sure. But I went ahead innocently with my questions. And I noticed as I asked them, it took each person longer and longer to decide. And I was so puzzled. All I wanted was a simple yes or no. But finally I knew I had to pick some word. Is it cloud, I said. And my friend thought and thought and thought. And finally he said yes. And everybody in the room burst out laughing. And then they explained to me that when I came in the room, there was no word. They had agreed not to agree on a word. Everybody could answer as he pleased, with only one proviso that all the answers should be consistent. So it was just as hard for them as it was for me. And this, to me, is like the electron in the atom. We used to think the electron in the atom had a position and a velocity, regardless of whether we measured it or not. Just as I thought there was a word in the room when I came in, and there was none. This is the strange sense in which we have a part in bringing into being that which we think is already there in the world around us. The world does not exist, quote, out there, the way Einstein used to think.